In this lesson, we are going to animate the galaxy we did previously. We saw that animating each particle is a bad idea. Animating the geometry buffer attribute on each frame is a bad idea because we have too many particles and we need to tell Three.js that we did update them, and it can we can have frame rate issues quickly. But now that we know how to do shaders, we're going to animate each particle by using a vertex shader. So in the setup, we have the galaxy that we had previously, but without the spin effect, because we are going to do the spin by animating it. And we are going to animate the one in the center faster, so we can have a spin creating automatically. You will see what I mean by that. So first, because we want to create our own shader, we need to replace the points material, which is over there, points material, by a shader material. And we can just do that. So let's go. We will have a lot of troubles, you will see, but anyway, it's good to learn. So first we replace by shader material and we get a strange result. First, you might not get something on the screen, all right? If you have a black screen, it's okay. I know that I have something visible. I have red particles everywhere. You might have nothing. We'll get back to that right after. Anyway, if you check the console, you will see that size is not a property of this material and size attenuation is not a property of this material. Thank you, Three.js, for telling us that. But because we are now using our own shader material, we cannot use those kind of properties. Those properties were for points material. All right, so we can just get rid of them and we will have to do it on our own. So just remove them to get rid of the warning, and we will have to handle the size and the size attenuation on our own. If you still have a black screen right here, it's perfectly normal. So yeah, it's because your GPU might be different from mine, all right? I think that most people will have the red points, red dots I have here, the red particles, but it's because actually, currently, the size is 0. Meaning that we didn't provide, we'll see how we can do that, but we didn't provide a size for the particles. And when the size is 0, some GPU will show a 1 by 1 particle, meaning that those pixels are just 1 pixel, I mean 1 fragment, but some might see 0, some might just see nothing because their GPU tells if there is no size, well, it's like there is nothing to see. We will fix that anyway by providing our own vertex shader. And we can start by providing those vertex shader. Remember, we have to do vertex shader and then provide the program. We can start by writing the program right here. I like to do that. I just write the program until it's working. And once it's the base is working, I put the program in another file, the shaders in different files. So let's go. Can you do it just like that without any help? So it looks like main. Then we are going to set the position. Yeah, we can use comments like that. Why not? So all about the position. Remember the matrices we need to use? We will have something like, it looks more like this. Anyway, we will have, I like to write them. We will have the model matrix, then the view matrix, and then at the end, the projection matrix, in order to place it on the clip space. Remember the box. So let's go. First, we are going to do vec4 because we need vec4. Those matrices are mat4. Remember that because we are using a shader material, we don't need to retrieve those matrices here. We don't have to do uniform mat4 model matrix because the shader material will do it automatically at the beginning of the code. So let's go. I'm going to call it model position. I like to use the same name or very, very close to the name of the matrix. So it's going to be model matrix. It's hard to write when the only color you have is green. It's a vec4. We need to convert the position to vec4 and provide 1 as the 4th value. And this one, this is the attribute. All right, and yet again, we don't need to retrieve the attribute because we are using a shader material. The next one is going to be, maybe I'm doing mistake here. Let's see. It's going to be view position. And I'm going to use the view matrix. and multiply by the model position. And it's a vec4, so I don't need to convert it to a vec4. And the final one is going to be the projected position. I prefer projection. I don't know why I started with projected. Anyway, let's keep using projected like in the previous lesson. And I'm going to use the projection matrix. I don't need those anymore. I can just remove them. And I'm going to use the view position. So as you can see, we use the position, we convert it to a vec4, we apply the model matrix, and we get a model position. On that model position, we apply the view matrix, we get the view position. On the view position, we apply the projection matrix, and we get the projected position. And at the end, remember what we have to set? The GL position, with this very strange syntax with the underscore and also uppercase. And we just provide this projected position. I know that you can really shorten this part, but anyway, I like to keep it this way so that we easily understand. And we are going to provide something else, this little part here. And you probably can guess what it is. And it's going to fix our problem, especially for those that don't see anything on the screen. So GL point size, be careful, there is a upper P and upper S equal 2.0, like that. And we can say, finger crossed, yeah, you should see something. If you still have a black screen, there is probably something wrong. Check the logs, check what you wrote here, and we can continue. So this was the vertex shader. It was hard to write because we don't have a syntax coloration. We're going to fix that. And as you can see, we choose 2 here. And this is the GL point size, and it's a fragment size. Remember the fragment? This is where you might have a different result too if you have a pixel ratio above 1. Me, I'm using a pixel ratio of 1, a screen with a pixel ratio of 1, meaning that 2 fragment, because I said here 2, is going to be 2 pixels. But if you are using like a high pixel ratio, like 3, 4, 5, something like that, you will have very small points because you have more pixels on your screen, and one fragment still is one fragment, and your fragments will be smaller, right? We are going to fix that anyway. So if you have smaller points, it's okay. We're going to fix that later. And then for the fragment shader, the good thing is that we just need to provide a color. So fragment shader, like that. And you just use the void main as usual and provide the GL frag color like that. And it's a vec4 because RGBA. And we are going to use, it looks like white. Okay, let's go for white. All right, you should see that. If you don't see white particles, pause the video, fix it, and get back to the video. So we are going to move those shaders in a different folder. We are going to do the usual. So inside the SRC folder, we are going to create a shaders. Yet again, we will only have one shader, but you might have multiple shaders on your project. So create a folder for each shader. I'm going to call it Galaxy. And inside this one, I'm going to create a vertex GLSL and fragment.glsl. Nothing new. We do what we've done multiple times already. Inside the vertex shader, you can take this whole vertex shader. So I just cut it and copy it. Be careful not to take the back coat. All right, don't take those back coats here. Just the code inside. Yeah, this one got messed a little. Anyway, let me get it right. All right, looking good. We can save. And then the fragment shader, we are going to do exactly the same and put it there like that. Okay. Don't forget to save the vertex shader and the fragment shader. I can show you in my folder. It's going to look like that. So you have your SRC folder, your script.js, the shaders folder, the galaxy folder. Inside you have the vertex.glsl and fragment.glsl. Save both of them. Let me check. Yeah, this is what we did. All right, and now we can import them. So we're going to fix that shortly. I can close the sidebar, and you're going to import them as usual, and we are going to call it Galaxy Vertex Shader. Yeah, why not? From shaders galaxy vertex GSL. This is just the path starting from the script.js. Then fragment. Be careful with uppercase, lowercase, stuff like that. You can log them. We will have an error, but it's an error linked to the material. So just go to the beginning. You can see that we got the galaxy vertex shader. I can try with the other one. So the galaxy fragment shader. I know that there is an error after, but it's because the material don't have any shaders right now. So we get the fragment shader too. All right, we just get what we wrote inside those. Then we can use them like that. So you just copy the name you imported here, you choose here. And we're going to move to the shader material, copy one here, copy another one here, like that. Be careful with the comma, we can save, and we get the same result. All we did here is move the vertex and the fragment shaders to different files, so we can write it easily. All right, cool. So first, let's talk about the size. That's a problem because at the beginning, we just wanted to animate the galaxy particles, so the stars, and now we need to handle the size and we will need to handle the color and stuff like that. Yes, because we are not using the points material, we need to redo everything that the points material were doing, at least everything that we need. The color, the size attenuation, handling the pixel ratio and stuff like that. Yeah, so let's go. First, the base size. We set the size to 2 here, and you can try with a bigger, not too big, be careful, don't burn your computer. As you can see, it's bigger, great. Let's get back to 2. Anyway, we want to be able to control this from outside of the vertex shader, like from this .gui. So we are going to create a uniform. You probably knew that. U size, because it's a uniform, I will use U, and I'm going to provide value. Don't know, 8. Yeah, why not? It's going to be bigger than the current one. You can save. Nope, let's not save the website. You can save the script. All right, we're sending the uniform, but we are not using it. Inside the vertex, you can retrieve the uniform. So you can do uniform. Which type is it? Well, it's a float. So float U size. You can save. If you do a mistake here, let's see, nothing happened. All right, so be careful. Maybe you missed you did a typo here. You won't get an error until you use that uniform. So you retrieve the uniform and you use it right here at the GL point size, and you get something like that. Yet again, if you have a pixel ratio above 1, you might see smaller particles. We are going to fix that. In real life, stars have very different sizes, and we need this. And this is like, I can tell you that when you do particles, add randomness, and it will do like a huge change. You will feel that it's more realistic if you have very different size from very small to much bigger particles. If you don't, you will see that it's fake. So always when you have particles, unless you have a reason to have the exact same size, add randomness in their size. And because we are using vertex shader, we can do that. I don't know if we could have do that with the points material. I don't think so. So right now we can add randomness, and it's going to be pretty easy. So let's go. So that we have very different size of stars. We are going to the geometry. And just like we created, remember this code? I can just show you again. We created an empty buffer geometry. We created 2 float 32 arrays, one for the positions and one for the colors. I know that the colors doesn't work. We are going to fix that shortly. So this is for the color. We don't really care right now. And then we loop through the stars. If we have, I don't know, 1000 stars, we do that 1000 times. And we fill the positions array for the X, the Y, and the Z. And then we fill the colors array for the R, the G, and the B. And at the end, we just send those attributes to the geometry. We are going to do the same. We are going to add some randomness. We are going to send a scale attribute. You can do like random attribute or size attribute, but be careful because there is size, there is a U size, maybe A size would have been fine, but because it's going to be random value from 0 to 1, it's not the size, it's more like the scale. It's up to you. That's not that important. Anyway, you can change it after. So let's go. First, we are going to create a new float 32 array. I'm going to call this one scales with an S because I'm going to send a bunch of scales. How many value do we need for the scale? Per vertex, where we just need 1. It's just a number from 0 to 1. So remove this part or use multiplied by 1. I like to keep that. I know that it's completely useless to multiply a number by 1, but I think it's clear. Someone looking at my code will say, all right, it's because there is only one value. It's not something that got forgotten or something like that. It's up to you. I know that it's completely useless. And we can add the scale. We can do it, let's do it after the color. So I'm going to do scale, and I'm going to fill this scales float 32 array at the I position, because I don't need to use the I3. All right, this is for when we need 1, 2, 3, 1, 2, 3. So X, Y, Z, X, Y, Z. Here it's just one value. So I equal math random. All right, I just fill it, and you can just test it. So we created it here, and we fill it here, and just test it. All right, always test the values, and we get something like that. So it's a huge array. We have 200,000 in it because we have 200,000 stars. If I look at the .gui and inside, always check like at the beginning, do you have random values? Yes. And always check at the end to make sure that you didn't mess with the loop. And remember, Chrome is showing you only chunks of the array, which is great because we don't have the full array visible in the log. It would be too much. And it's working. We have random value from the start to the end. Great. We can remove the log and then add a new attribute. I'm just going to copy it. I'm going to call it A scale, A for attributes. We are not going to rename those because those are handled by the shader material with those name. Like the shader material, the code which will be prepended will use this name and this name. And I can show you, maybe I will show you later. So for the A scale, don't forget to provide how many values for one vertex. In our case, it's just 1, just like we shows 1 here. We save, finger crossed, no error. Let's continue. To retrieve the vertex attribute, so I wanted to show you the position and the color. See, I did one mistake. I removed the semicolon. You don't have to do it. I just want to show you. But when I want to have a quick look at the code, because I'm not sure of what is being prepended to my code, I just do one mistake, and then Three.js will log the full program. And I will be able to maybe find the problem, not the problem I did, but the problem I have, the thing I want to know about the code, the prepended code. And that's the part I'm talking about. So we have the position, the normal, and the UV. And where is the color? Well, it's a little later here. And it's inside this if def use color. We didn't see that kind of if. I can just talk to you about this. It's a conditional, but when the program will be compiled, meaning that this part might not be even available in the shader, because if this define, it's a define, this one, is set to false or doesn't exist. So if this define doesn't exist, this code right here won't exist inside the shader. So it's better for performances. Like we compile only the part of the shader we need. Anyway, I won't go into details about that. It's like a condition, but at the compile moment. And here is our attribute vec3 color, which is why we cannot change those names. We have to keep position and color, because in that part it's color and here it's position. Anyway, let's move forward so I can get back to my code without error. And what I will do now is retrieve the attribute. So this attribute, it's A scale. Is it a vec2, vec3? Well, it's a float because it's just one value, and I will use A scale like that. No error. Great. If I do a mistake here, like I don't write the right thing, no error again. So be careful. Maybe you did a mistake here, and as long as you don't use it, you won't see the error show up. And what we will do now, let me check. I just think we're going to multiply it. Yeah, that's all. We're going to use the A scale and multiply the U size by it, just like that. You will see this And this is so much realistic. I know it's just white squares. We're going to fix that, but it will give you like realism easily just by adding randomness. And we can do that now that we master the shaders. So let's talk about the pixel ratio. We are going to make sure that everyone can see the same thing. So as I said, if you have the size we provide here is a fragment size, meaning that if you have more fragments, well, the fragments will be smaller. If you have like a pixel ratio, I don't know, of 3, the fragments will be much smaller and you will see smaller particles. So we need to fix that. There is many ways of fixing that. We are going to use, I think, the most simplest way of doing it, which is not exactly what Three.js do to fix that, but anyway, it's kind of the same concept. First, we need to get the pixel ratio. And you know how to get the pixel ratio. Like if I don't do it, just follow me on that. If I do window, device, what is it? Pixel ratio. You don't want me to show it. So window, window, device, pixel ratio. I don't know why he doesn't. And I get 1. All right. So maybe we can use this one and simply multiply the U size. Where is my U size? It's here. By that. Don't do it. This is a mistake. Do you know why? Well, because the pixel ratio, we did provide it here. Remember when we set the renderer, so it's here in the resize, but also here. When we created the renderer, we also provided, well, the size of the size we need for the canvas, the render, but also we provided the pixel ratio here, and we set a limit to 2. Because we don't need more, we will have performances issue if we do above 2, probably. So we did like a limit, like a clamp to 2. So if you provide the window device pixel ratio without the limit, you will have a problem because it will be different. So maybe you can think that, yeah, we can just take this part. So don't do it again. It's not the right solution, and use it inside here. So I do multiply by that. You could do that, you will get the right result, but if you change it somewhere, you might forget to change it here. We have quite a simple code here, but once you do like a real project, you will have many, like 1,000 lines of code, and you will probably forget to change this one. What we can do instead is retrieve automatically the pixel ratio from the renderer, all right? So that if it change inside the renderer, we will get it automatically. And if the limit change, well, we get it from the renderer. And we are sure that we get the same one as the renderer. And there is a method to do that. What we can do here is multiply by renderer get pixel ratio. And you get the pixel ratio from the renderer itself. If it did change, well, you will get something different here. All right. I can save and I will get an error, unfortunately, because we are doing a JavaScript mistake. We are trying to get the pixel ratio, to use the method get pixel ratio from a variable that doesn't exist yet. Why? Well, because this is inside the generate galaxy, and we are calling the generate galaxy right after, right here, but the renderer doesn't exist yet. So this is just a JavaScript mistake. What we can do here is take the generate galaxy function call. So just the call, not the whole function, just the call of the function. And we can move it, well, at the end. You can put it like right before the tick, probably maybe after the tick. Let me check. No, not after the tick. We will have a problem later. But anyway, as long as you put it after the renderer, I will do generate galaxy with just generate galaxy like that. This way, when I call generate galaxy, I use the renderer here and it does exist. All right. So move the generate galaxy after the renderer. So all this part you can save. You have to refresh if it got stuck. And anyway, now you get the same result as me. Because if you have a pixel ratio of 2, well, you will get 2 from the renderer. Let me check, it's over there. We get 2 and the particles will be twice as big. And if you had 3, because maybe you didn't put the limit to 2 just like we did, you will have a size 3 times bigger, but your fragments will be smaller, so we will get the same size. Anyway, let's move forward. Yeah, we did fix that. All right, we have a problem right here. Just focus on one particle and try to zoom on it. The zoom is way too sensitive. Anyway, you will see that whatever the distance is from the particle keep the same size. All right. If the particle size is 8, if you're far or if you're close, it will be 8. Meaning that if I'm very close, you can see that it's still the same size for each particle. So we need to fix that. It's the size attenuation. Remember that we did use on the points material. We just have to set size attenuation true. That was easy. Unfortunately, we have to do it on our own here. It's going to be very interesting. I could just provide you a formula, like one of the formulas I used to, I'm using, but still I want to show you something. Right now, we need a cool feature, which was the size attenuation from the points material. And we don't know how to do it. We can do a search on the web, we can use formula, we can ask the Three.js community and stuff like that. Or we can just get the code from the Three.js shaders. And this is exactly what we are going to do. This is a way to dive into the Three.js shaders and start to understand how Three.js is working. It's always great because this way you will have more control and you will understand Three.js in order to improve Three.js. So let's go. I will show you how. What you can do is go into the node module. So it's the forbidden folder. You can check on it, just don't change anything inside. So go to the node modules, search for the three dependency, and we are going to find the shaders inside Three.js. And the great thing is that the Three.js folder is so well organized. It's really easy to find what you want. So it's inside the 3 src renderers shaders, and this is where all the shaders are. Almost all the shaders will be here, and you have shader chunks and you have shader lib. There is not that many shaders. I mean, yes, there is a lot, but for such a huge library, I think it's okay. And they are well named, meaning that you can easily find what you're searching. I repeat that we want to do the size attenuation that we had with the points material. And check that out. We have points frag glsl gs, strange, points vert glsl gs. So this is the fragment shader of the points material, and this is the vertex shader of the points material. And because the size is handled in the vertex.glsl, what we need is in here. All right. Let's have a look. As you can see, we have include. This is very specific to Three.js. This is Three.js way of handling chunks of code. And those chunks of code can be found inside the shader chunk. Like if we have a common, let me check. Yes, we do have a common. If we have color parse vertex, do we have color parse vertex? Yes, absolutely. So we get those chunks. All right, cool. This is the way of Three.js to reuse part of codes. And here, if you just scroll a little, you can find these. Use size attenuation, just like we said earlier, this is like a compiling condition. We don't really care about this because we know that we want to use size attenuation. What we want is inside of it. And we have a Boolean is perspective. So this is a Three.js way of testing. All right, do we need perspective? If not, well, we don't need to use like size attenuation. So okay, so if it's not a perspective camera, probably it won't work. The size attenuation won't work. We don't care about this. We have a perspective camera. We want size attenuation. So we don't care about this. We don't care about this. We don't care about this. All we need is this part. And what inside this part? This is kind of the hard part because you will have to study and try to find the scale. Where is the scale? No, the scale. Oh, it's here. It's a uniform. All right, fine. And the MV position. Well, I don't know. I will have to check on those here, those here, those here, those here. I think it's going to be over there and over there. There is not much inside the begin vertex chunk, but there is everything we need in the project vertex chunk, but we will have to also check the uniform. So you might spend few minutes, maybe a few hours until you find exactly what you want. Anyway, I'm going to tell you what's happening here. It's not that complicated, but we are not even going to explain the mathematical solution. We are just going to take it and use it. We'll see the result shortly. So the part we need is this part, and it looks like this, GL point size. We multiply so it's the scale divided by the minus something called MV position. Maybe you can guess what MV stands for. And you should get the size attenuation. According to 3GS, the scale, it's kind of the current, it has something to do with the height of the render. This is the way of 3GS to handle, like if you have a small screen or a big screen, the particle will be stretched according to the size of the screen. So if you have a huge screen, you have huge particle, and if you have a small screen, the particle will look smaller. So that you get like the same result regardless of the size of the screen. We are not going to do that because I'm okay with having like particles. The particles will keep the same size, and the size will be well, it will look bigger if you are on a small screen. Anyway, let's not talk about this. We are just going to replace this by 1.0. Don't do it. I'm just showing you what we are going to do with that formula. So we are not playing with the scale. We are just going to use 1.0. And this part, this is an interesting part. M and V stands for model and view. So it's the model view position. And we have this. MV will be for us the view position. All right, because we applied the model matrix to get the model position, and we applied the view matrix here on that model position. So in a way, we get the model view position. Maybe we should have called it like model view, and then this one, don't do it. It's going to be model view projected position. All right, let's not do that. It's way too long. Anyway, the MV variable, MV position variable, for us, it's the view position. Then we know how to do that. We have everything we need. This is the GL point size, well, it's the GL point size. We multiply it by 1.0 because we don't want this kind of scale according to the 8. And we just replace by view position. Well, let's go. I can just take it, move it there, and do the exact same formula. So it's going to be GL position multiplied by, and then I will remove those spaces. Here I will use 1.0 because I don't want to play with this value. And here it's not MV position, it's the view position. And we use the Z. And don't forget the semicolon at the end. Finger crossed. Let's see. It seems to be different, and see the one very close to the camera. Yes, they are way bigger. It's working. The one at distance are very small, and the one close to the camera are much bigger. We got the size attenuation back by using 3GS code. So thank you 3GS for providing us this formula. Anyway, this is one way of doing. If you didn't understand exactly what we did about the size, about the height, the MV position, it's okay. You can just use this formula to get the size attenuation. All right. So let's go a little further. Instead of having those squares, we're going to draw a shape inside of it because we can. Let's do it. We can do it. So let's do it. We are going to draw a pattern, and we have choice like what to draw inside of them. We can use what we did in the previous lesson, so the patterns lesson, and we are going to, I think, to draw 3 patterns and just keep one of them. So remember what we used to draw patterns on the plane? We used the UV. Yes, so we had to send from the vertex the UV coordinate as varying VUV and use them inside the plane. But right now, we cannot do that because it's not the same situation. Each vertex will be a particle. We cannot just send the UV and it will be interpolated as a VUV. We cannot just do that because it's not the same. Each vertex will be a full plane. So how do we send it? Well, actually, it's much easier. We already have it inside the fragment. If you want the UV, let's say, let me find a big plane. Yeah, like this one. Yeah. If you want the UV of this plane, you don't have to send a varying or stuff like that. You can just use GL point code inside the fragment. All right. So you can test it, put it there. I will use 1, 1 as the third and fourth value, and we will get that UV. Look at that, looking great. It's not exactly the same because we are using a blending. If I remove the blending, don't do it, but I can show you. Now it's looking the usual shape. It's not exactly the same, meaning that, by that I mean that the bottom right is the white, usually it's the top right. It's the same because we are going to draw circular shapes, so we don't care about that. So we can get back to the additive blending, and we are going to use the GL point code to draw shapes inside of it, just like we did in the patterns lesson. I told you it can be useful to do that. By the way, you can just try. So first we're going to draw a disk pattern. So let's go. I have some drawings. We want to draw a disk pattern. It will look something, I cannot draw a circle. Anyway, let's try something like that, 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 and that. It's okay. All right. We want a simple disk, and this will be filled. How can we do that? Well, I gave you the process. First, we get the distance between the GA point code. So this is the coordinates you can see. We get the distance from this coordinate to the center. So let's say we want to draw, let's say this part. We get the distance from the center to this. And we get a value, something like, I don't know, 0.4 maybe. So it's going to be 0.4, like that. So this will be 0, this is 0.4, because this is the center. All right. We apply a step function on it because this will go like further. So this will go, I don't know, maybe something over there like 1. We apply a step on it, and the step limit will be 0.5, meaning that if it's before 0.5, so we decide on 0.5 as the limit of the step. If it's 0.5, this will stay like 0. And if it's above, we'll get 1. So all this part will have 0. We have a value that goes from 0 to 1. We apply a step on it with a limit of 0.5. If it's below 0.5, we get 0. If it's above 0.5, we get 1. So it should be around here. And obviously, this is not what we want. We want it to be visible here and invisible here, where we are just going to invert it, do 1 minus the step in order to get 1 here and 0 here. I know it was maybe too fast. Go back to try it on your own. Go back to the patterns lesson if you need to practice those. Anyway, let's do that. So we have the coordinates. So let's go. We are going to use the same technique as during the patterns lesson and use a strength. All right. So float strength. We are going to draw 3 patterns. Equal, we get the distance. There are other ways of doing that, the distance from the center, but anyway, let's use that. So it's the distance of the GL point coordinate. So if we are, I don't know, taking care of this guy here, we get where the distance to the center. So we get 0.4 if it's this one. So the distance and the center, well, it's vec2 0.5. All right, because our GL points look something like that. There it's 0, 1. So this is on the X, and on the Y it's something like that. So it's 0, 1 on the Y, which is not true because actually it's the opposite, it's going downward, but it's the same because we are drawing like circular shapes, so it's okay. So the center here will be, sorry, too far. 0.5, like that, 0.5, and the center here will be 0.5, like that. All right, so the center here is 0.5, 0.5. So let's go. We provided, we want the distance between the GL port chord and the center. Once we have this, well, you know what? Let's just show it. I'm going to provide this vec3, this, and we get something like that. And it's already working, as you can see. Let's try to find one. So it's a good start. We get the distance from the center to the point we are drawing. And we get something like that. All right, it's a good start. It's not, we want a disk. It's not a disk yet, but it's a good start. And then what was said is that we are going to use a step so that we get instead of this gradient, we want like a clean cut. So we're going to do strength equals step. The first value is the limit, so 0.5, and the second value is the value, well, the value that changes, and we get, yeah, it's a good start too. It's working, like we have a clean cut, but it's the opposite of what we wanted. So what we can do is invert it. It's not exactly inverted, but anyway, 0.1 minus strength, so that we get the opposite. What do we get? Yeah, we get circles. This is one way of doing circles. We could have sand texture, all right? And texture is actually, it depends on your texture, but it can be better for performances. Anyway, we did draw a disk. Great. Next one. A disk is great. Seeing from far, it's okay. Maybe we need like bigger particles, but it's great. But we need something like smoother on the edges. We are going to create a diffuse point pattern. I call this diffuse point pattern. I don't know if it's the exact name, but anyway. The idea is kind of the same thing. So diffuse point, like that. You can comment this part. We start with the same. So float, we get the distance between J point chord and the center. All right, let's draw it. We get the distance from the center, like this. So this will be somewhere over, I think it's going to be close to 1, maybe a little further, like 1. 0.5 is going to be over there. I'm going to put it above. So this is 1, this is 0.5, and this is 0. All right, we get this value. So it's the distance from the center. Then we multiply it by 2, because as you can see, when we get to the edge, it's only 0.5. It's a problem. We want it to be 1 when we get to the edge. So we multiply it by 0.2 so that we get something like 0, 1, and we don't care if it's 2 here. We don't care of this part. As long as at the edge we get 0. This is so that this part will be 1 at the edge, all right? Because right now this part will get to 0.5. It's not good for us. We need it to be 1. And then we invert the value. So that we get, I can use purple, why not? So that we get 0 here, and so that we get 1 here. So it's this part. I know I'm doing like a parallel thing, but we're still talking about this part from the center. So we get 1 and 0 quickly, and right here it's maybe minus something. We don't care. We don't care about this part as long as we have 0 at the edge. And this way, well, here it's going to be 1. Can use another color. So everything close to the center will be close to 1. Over here it will be maybe 0.3. Over here maybe it will be like 0.45. And here it's going to be 0. Yeah, I got it wrong. Sorry. It's going to be 0.1, very close to the edge. And here it's going to be 0. And here it's going to be minus something, 0.5, I don't know, I don't care, we don't care, as long as it's 0 on the edge. So we get this, and little less, and little less. We'll get a diffuse point. I'm bad at explaining this, sorry if I said it wrong. Anyway, maybe by doing it, you will understand. So first we get the distance from the center, it's exactly the same. So strength equal distance, GL point chord, and the center is 0.5. So it's the distance between the fragment we are trying to draw. So it's the coordinate on the particle, and the center. So it's the distance between those. We can just show it as always. So I already have my strength here. Remember, we already have this one. This is the value. All right. Let me check if I can get one better. Yeah, like maybe this one. Okay. 0, because it's the center, it's the distance from the center, and the further we go, the higher it is. Then we're going to multiply it because we want it to reach 1 as soon as it touches the edge. So strength multiplied by 2, 2.0, don't forget the 2.0, and we get something like that. See? It got close. Can I get one better? Please. Yeah. We got close to 1 faster. we got to 1 faster so that at the edge, it's already 1. And then what we do is that we invert it. We do strength equal 1.0 minus this to have the opposite, and it will look like this. Much better. We get a diffuse point. I think it's great. I would probably have used it because seeing from pretty far, it's okay. All right. We don't see much and it's going to move. So really, we won't be able to see much. But anyway, we are going to go even further and draw a light point pattern. Still, yet again, I don't know if it's the right way of saying it. Light point pattern. And I think the start is kind of the same, and I'm going to explain you. We start with the same thing. We get the distance. So this is the distance again. We invert the value immediately. I'm going to do some drawings after. Maybe it will help. So we invert it right away. Minus strength. Because we don't really care if we reach the edges soon. So we get something like that. As you can see, we can still see the edges of the square because the value is not like fading fast enough. And right now, what we are going to do is apply a power on it. So the strength equal power. So we apply on the strength and we apply a huge power. 1.0, something like that. And you will see what we get. And look how beautiful they can be. I know they are too small. We are going to increase the size. But now they look better. How do they look better? Well, it's because we have kind of the same effect. So we have this kind of, remember the drawing I said, it's a diffuse, but it's a linear diffuse, meaning that here is going to be 0, here is going to be 0.5, and here is going to be, I do it again. Here it's going to be 1, 0.5, 0. It's linear. By doing the code we just did, and I'm going to explain to you, we get like a huge concentration of light here, and it fades really fast. And here we can already barely see it. So it just fades faster. It's not linear. Like if I were to write the color, it would look something like, let me put that, like that. If the color is fading, let's just focus on one axis. The color will be really strong here and then fade really fast, like that. So the color here will be really strong and fade really fast. And it's exactly what's happening here. By using the power, you can just test value, do math power, so po, like that, and use, I don't know, like 0.5. So it's at the 0.5, so it's over there maybe. And apply a power on it. And here is the result. We get a very, very, very small value really fast. Let's use 1. So 1, it's nothing. Like there is nothing. It's 0.00000 something. But if you're close to 1, see, we get something like 0.9 will be visible. And if we get even closer, like 0.95, we are getting close to 1. And if we have 0.99, well, it's 0.9. What we get, I can again show you by drawing. This is the value. We have 0, 1 right here, and we get 0, 1 right here. Currently, what we have is a linear thing, meaning that the value just drops like that toward the destination. All right. If you provide 0.5, you will get 0.5 right here. All right. If you provide 0.5, you get 0.5. This is a linear value. What we are going to do here with the power is something like that. So that if you provide something very close to 0.1, you will still get 0.1. Oh, it's the opposite. Anyway, you kind of understand that we are doing here. If the value is close to 1, you will get something close to 1. But very quickly, the value will drop, like very fast. And at the end, you can barely see it. This is just a way of using the power. And if you increase the power, we did use 10, I think. Yeah, it's 10. If you use less, like, I don't know, like 2, you will get something like that. So we have less effect. And if you use, I don't know, like 30 or 20 or something like that, you will get even more squeeze like that. It's really hard to draw it. More like that. So you can control how much you push the value close to 0 and fast to 0. So yeah, as you can see, these are my limits. I'm bad at explaining this. You can play with it. Just use, I don't know, 2. We see that it will look more like the previous one we had. You can add, and we can see the edges. Be careful with that. So use, I don't know, maybe 5. I think 5 is looking great too. Yeah, this one is looking great. I'm going to use the one from the lesson, which is 10, which is probably way too much anyway. And because the values, we cannot see much of them because we can only see kind of the center, what we can do is increase the size. So go to the script, and instead of 8, you can put, I don't know, like 30. And we get this, and they are looking great. They are looking better. The problem here is that we are using like huge plane, and we can just see like the middle of the plane. We can barely see the edges. Like maybe this one is doing something like that. Maybe this is the size of the particle. So this is bad for performances. But still, I wanted to show you that. So we did it. But keep an eye on the performances. Right now, if you add a lot of particles, your computer might start struggling. Then, so we have beautiful particles, we have the pixel ratio, we have control over the size. Let's get the color back. So if we want to get the color back, remember that we sent the color here, so it's a set attribute color. Then we need to get it back, something like attribute vec3 because RGB, and get the color right here. And we get an error. Why? Maybe you know why, but because we already have this part in the code, because we are using a shader material, and the shader material prepended this part in the code. And you can see it there. It's inside the use color. It's this one. And we add it again, so this is a mistake. Let's remove our attribute, and we can just use it. And when you do vertex colors true, it will use this part. All right, it will add the attribute vec3 color. What we did here will be only added before if we set the vertex color to true. So be careful with that. What we need to do, because it's about putting a color on it, well, it's inside the fragment. We don't have access to attributes in the fragment. We need to send them from the vertex to the fragment. We can do it with a varying. We're going to do vec3. I'm going to call it vColor. And at the end, well, you know what? Let's use this way of writing stuff. Well, color, there won't be much in it. So it's vColor, and we say vColor equal color. So this is the attribute, and we put it inside the vColor. We save, we have a warning telling us that we added a varying without using it. So take the varying declaration, add it to the fragment. So still a warning because yes, we retrieve it, but we are not using it, and then we can just use it here. So there are better ways of doing what we are doing right now. I know that, but I want you to use the mix. So let's go. What we want to do is do a mix. So we're going to create the final color. We have the strength by using like the light pattern we did here. So it's just a strength value. Okay. What we are going to do is vec3. We want to create the final color. So final color. We'll do color, and we want to mix between black and the varying. So it's going to be vec3. How do we create black? Well, it's 0.0. And the vColor, depending on the strength. So we do a mix. We did quite a lot of mix. We mix from black to the color by using the strength. I'm not going to explain this too much. And then we can just provide this vec3 color to the RG and B of the frag color. We don't play with the alpha, and we get the color back. And it's looking even better because of the pattern. Yeah, it's looking really great. All right, cool. So it's looking great. We did the mix. I know there is better solution. Like we could just have used the vColor here and use the strength here. All right, we can get rid of this one, and don't forget to activate the transparency. So we do something like transparent true. So I know, yes, it's kind of the same result, maybe a little easier, but I wanted you to use the mix, which is why we are doing this. So keep on this version, it's okay. In terms of performances, it's fine. It's time to animate. This was the original goal. We kind of lost ourselves by trying to fix the size attenuation, get back the color, stuff like that, and change the pattern. But now we can do it. We can animate our galaxy. So we are going to do a time-based animation, as always, where we are going to send the time to the vertex shader. So let's go. You know how to do that. I'm going to call it uTime. You can call it whatever you want. Value 0. We start at 0. And then we update this value in the tick. So let's go. I'm going to do update material because we are only one material. And I will do material uniforms uTime. We update not the uniform, but the value of the uniform. And we can use the elapsed time, which is how many seconds spent since we refreshed. All right, it seems fine, no error. Now we can use the uTime inside the vertex. And it will be only inside the vertex because it's all about moving the vertices. So right now, I don't think we will get back to the fragment. So first we need to retrieve it. So float uTime, just like that. And what I like to do is just test it. You can do it with me. Just, I don't know, model position y plus equal uTime, just to see if it's working. Yes, as you can see, my galaxy is moving, it's going up, which means that the uTime is well added and used here and retrieved here. So great, I removed this part, it's not what we wanted to do. So our galaxy, we need to rotate, as we said earlier, we're going to do a rotation and the particles at the center will rotate faster than the particle on the outside, and we get this kind of spin effect and you will see the spin create itself, which will be great. Anyway, we are going to animate the vertices only on the X and the Z. Why? Well, because as you can see here, we don't need to make the particles move up and down. All we need to do is move them on the X and the, I used the wrong one. Anyways, it's okay. And the Z, like that, all right? The Z and the X. We don't need them to move up or down. It makes no sense. It's not useful. You don't see like the stars doing stuff like that and dodging other stars. So it's kind of strange. So we just rotate this way. Here is the idea. It's not that complex, but because I'm bad at all kind of angles, trigonometry, stuff like that, it will be hard to explain. So this is my fault. Sorry. Anyway, here is the idea. We're going to take one particle as an example. I'm going to say, I want to animate, let's say, this particle here. So maybe closer, like this particle here. Or maybe further, actually. Let's animate this one here, this little guy here. First, we're going to calculate the particle angle. So the angle, what angle exactly? Well, it can be anything. Like, let's say this is the 0 value, or maybe it's the one over there. We're going to take this angle. All right, so maybe it's this one actually. So we take just this angle. I'm going to take more like this one. I will calculate this angle. I will also calculate the distance. So the distance is going to be from the center. This is the distance from the center. All right, we'll get two values, the angle and the distance from the center. We're going to increase that angle, meaning that we want the particles to spin. So this angle, this arrow here, this angle, we are going to increase it. And the question is, how much? Well, we're going to increase it depending on the uTime and the distance. So at the beginning, every particle will be at their initial position. And the more the time passes, so the bigger the uTime, the more the particle will rotate. So at the next frame, it will be there and there and there and there, and it will rotate. And the speed of the rotation will depend on the distance. So that if we are rotating, let's say, a particle far, where the particle far will not rotate much. Like on the next frame, it will be there, next frame, it will be there, next frame, it will be there, next frame, it will be there. But the one, like really close, like, I don't know, let's say this one, see how close it is to the center? Well, we calculate the angle, so it's something like that. And we increase the angle, but much faster, like that, and then like that, and then like that. So this one will go faster because it's closer to the center. And because they will go at different speed, we will get that spin effect. All right, cool. This was my attempt on explaining to you. Let's go, we can do that. So first, as you can see, we need the angle and the distance from the center. To get the angle, we can use the ATAN. I don't know how you say. So ATAN is the arctangent function. I provided you a link. As always, if you want to learn more, you can go to the links panel and take this link. It's from the Book of Shaders, and it's just, they have the Book of Shaders glossary is just great. So have a look to this one. And this, you provide an X and a Y. So for us, it's not X and Y, it's X and Z. Or Z and X, it's the same. It doesn't make a lot of changes. Anyway, you provide X and Y, let's say Y, and it will give you the angle. All right, so you can just like provide, let's say, so this is the one. So this is the X, all right, because it's over there, and this is the Y, so it's over there, and you will get an angle. It will provide you like the let me show you this angle using ATAN. All right, let's go. Let's do it. So yeah, because we want to update the model, it will be over there. It will do spin here. So first we need that angle. So float angle equal. We just use that ATAN. ATAN just provide you the angle. You provide two coordinates. ATAN will give you the angle. So model position X. Be careful, all of this will work because our galaxy is at the center of the scene. If it's not, you will have to do some offset and stuff like that, but our galaxy is at the center. Then model position Z. It will just give you an angle. We cannot test it. I really want to do like console log or stuff like that, but we can't. Let's just try to get everything. The second thing we need is the distance from the center. So this particle, I want to know the blue line. So it's the distance from the center. This one is not that hard. We can just do float distance to center. Don't use distance because distance is a method. So you cannot call your variable distance. You can, but you will break the function. You won't be able to use the function later. Because everything is centered on the scene, it's at the center of the scene, well, we can just get the length of the position. So length, model position, xz, or zx, it's exactly the zx, it's exactly the same. So yeah, because everything is centered on the scene, the distance from of that particle, well, it's the length of its position. So we have the two values we need. What we need to do now is calculate an offset angle. We want to know, according to the time and the distance, how much does the particle should have spin. So what we can do here is float offset, so angle offset, why not? Offset angle offset is going to be 1.0 divided by the distance to center. It's not just the distance to center, because if you do just the distance to center, the one on the outside of the galaxy will run faster, because distance to center will be a small value. So this one is close to the center, the distance to the center will be a small value. And here it will be a bigger value because it's further. That means that those one will rotate faster, which is not what we want. We want the one on the center to rotate faster. What we can do here is exactly what I've done here is 1.0 divided by the distance to the center. We get like kind of the opposite, which is great. And we multiply it by the U time, because this way the offset will be bigger with the time. Everything will start to rotate because we use the time. And because this one is just too strong, you can just lower it a little. We see that this will get handy shortly. Just save, make sure that you didn't do any mistake. It's always something, point something, because we are using floats. Don't forget the semicolon. And I think we have everything we need. But we are going to do a small mistake. So because we calculated the angle offset, so this is the base position, we applied an angle that depends on the time and the distance. Great. We can update the angle and do angle plus equal angle offset. We could have just, oh, sorry, what did I do there? Yeah, angle offset, like that. We could have directly applied this formula inside the plus equal something, but anyway, I like to have clean variables so that you can understand easily. We can just save. Nothing changed because all we did here is update a variable inside the vertex. So it's not working. We don't get any result. What we need to do now, because we now know the new angle of the particle, so we calculated that according to the u-time and the distance, this particle is supposed to be here. But all we have is an angle, this angle, like this. How can we position the particle? Well, we are going to position it on a circle. We have an angle. We want the coordinates. We are going to use cos and sin. So let's go. I'm going to do model position, and it's on the x and the z, because we are just animating everything on the x and the z. X equal, we use cos of that angle. Remember that we changed that angle. And sin of that angle, so this one is for the z here. Usually I just tweak them until I get the right result. We use the same angle on cos and sin, and this is the way of positioning something on a circle. You can save. What do we get? Well, we get this. This is looking great, like it's Portal. You can traverse the universe with this thing, so it's looking great, but this is not what we want. What did we do wrong here? Can you guess what we did wrong? When positioning on a circle, we get a position on a circle with a radius of 1. So this is what happened here. We use cos and sin. We get a position on a circle with a radius of 1. We forgot to apply back the distance. So all we need to do is, like maybe this one here got position on here. So because it's 1 distance, and this one here got also position here, and we get like everything positioned at a distance of 1 to the center of the galaxy, something like that. We get a lot of things here because we forgot to put back the distance. So to just put back the distance, well, we already have this value. It's the distance to center. So if this one was at this distance, maybe it got here. Well, we are going to bring it back, so we just multiply by the distance again, so it gets back to the initial radius. So to do that, you take the distance to center and you multiply the cos and the sin like that. This is the way of changing the radius of a position on a circle. And look at that. Yeah, I could watch it for hours. I like this one. All right, cool. We are almost done here. We just have a small problem. Just look at it for maybe a few minutes. It's going to be quite long. Anyway, we'll be able to see the problem quickly. Just wait a little more and you start to see the problem. It's getting stretched. So right now it's not much of a problem. It depends on the size of the galaxy, stuff like that. I actually like it this way, but it's true that we have a problem that, see, it gets thinner here. Look at that. It gets thinner and thinner, and it won't get better. And after a few minutes, it will have like a ribbon. It will look like a flat ribbon doing something like that. All right, we need to fix that. Well, first, it's because we are just like stretching the thing, and at the end you get a ribbon. Maybe what we need is just to add some randomness. But we already added some randomness. Remember in the script, right here, let me check, where is it? Yeah, it's right here. We added randomness here, so random x, y, and z, and we added to the position. But this randomness was before doing the spin, and then the randomness will get stretched too, and we will get this ribbon effect too. So what we need to do now is apply the randomness after doing the spin. But wait, we applied the randomness on the base position. How can we apply it after? Well, we are going to have to remove this randomness from the base position and create a new float32 array, a new attribute, and use that attribute after doing the spin. All right, I repeat. Instead of applying the randomness before doing the spin directly on the base position, we're going to remove it from the base position and add it to an attribute so that we can apply the randomness after the spin. Let's go. So first you can remove it here. So remove the randomness here, remove the randomness here. I can put 0.0 or 0 and remove the randomness here. What do we get? We get something like this. All right, because we remove the randomness. That's cool. Next part, we are going to use the randomness back by creating an attribute. So we are going to do random, let me check, it's going to be, yeah, just randomness. Oops, randomness. It's going to be a size 3 because the randomness can be on every direction. So randomness multiplied by 3. Then we put this randomness here. So maybe I can just move it after like that. Yeah, randomness. We're going to use those values and we're just going to use them. Let me check what I did here. Yeah, inside the randomness. So let's go. Randomness at I3 plus 0 equal random x. Then plus 1, so the y, and the z, 2, so x, y, and z. All right, the randomness is the same. I just took this value and I put it back, but this time inside a net attribute. We can save, just make sure that we don't have any error. Okay, great. Then we can send it to the geometry buffer attribute, to the geometry buffer geometry, sorry. So it's going to be a scale, sorry, a random. I think it's a random. Let me check that. A randomness. Getting tired here. Sorry. So it's going to be the randomness array and the size is 3 because we want the randomness to be on 3 axes. So we just use size 3 like that. We save. We get the same result, but right now we can retrieve the randomness here. And we can do it like that, vec3, because they have a size of 3. We called it a randomness, so this is the name of the attribute. We get something like that. And then we can apply it back after the spin, so it's over there. And we're going to call it randomness. How can I apply this? Well, I can do model position x plus equal randomness x. Then the y, you can guess that there is a shorter version. Then the z. Let's just check if this one is working. And yeah, we got back the randomness. And because we applied the randomness after, we don't get this ribbon effect. See, there is like chaos inside because we applied the randomness after. And it's looking great. But there is a much more simple way of doing that. We can do model position plus equal. I will do a mistake. A randomness. I will get an error. Can you guess what I did wrong here? This is a classic mistake. Pretty hard to find this one. Maybe check the error. Assign cannot convert from int high 3 component vector of float to high 4 component vector 4. It looks like we are trying to convert a vector 3, so 3 component vector, to a vector 4 component vector. And yes, it's exactly the problem. We are adding a vector 3 to a vector 4. We don't want to play with the 4th value of the model position. What we can do is x, y, z. We just add the randomness x, y, z to the model position x, y, z. The x will be added to the x, the y to the y, and the z to the z. We save and we get the same result with just one line of code. And yeah, it's looking great. You can play with the randomness, parameters, randomness. Anyway, you can do whatever you want. You can create the galaxy you want. It's looking just fine. And right now it's animated by using Vertex Shader and the performances are pretty good. I think if you have performances issues, it's more about the fragment. All right. It's what we did here. We have huge particle and only draw like a small point at the center, but with a kind of diffuse effect. This is bad for performances, so be careful with this one. But the vertex part is, trust me, it's okay in terms of performances. And we can have much more, and it looks great. That's cool. All right, it's the end of the lesson. I will see you in the next one.